Hello there, Khaled Al-Malawani here. Today we're going to talk about how to operate and set up the MPU6050. You may hear that the MPU6050 by different names, whether it's the GY521 or the MPU6050. Let me clarify that for you. So the GI521 is actually the board. So the board layout for the IMU, which you can see right here, is the layout that you see right here is known as the GY521 board layout. However, the actual MPU, which will be the square right in the center here, is just the MPU 6050. The MPU 6050 has 6 degrees of freedom, which means a degree of freedom is basically a measurement. So in this case here, whether every degree of freedom is dependent on what axis you can measure, and in maximum you can have is 9 degrees of freedom, which will be XY axis of the accelerometer, XY axis of the gyroscope, and XY axis of the magnetometer. However, for the MPU 6050 here, we have 6 degrees of freedom, and the ones that the MPU implements here is the XYZ of the accelerometer as well as the XYZ of the gyroscope. So that's a bit of information here about the MPU 6050. However, something more to note, and it is always good practice to include here, is is that you should always read the data sheet. So in this case here, I will show you the data sheet. So here is the data sheet for the MPU 6050. It's a pretty big document, much bigger than previous data sheets that we've seen. And if it's important to always have a good read of the data sheet to be able to implement things better here. But noting something here is that Arduino is a very popular language, which means the forum is huge. In other words, that other people already tried to implement these ideas. However, it's always a good idea to read the data sheet, but you could also look online for different codes and different implementations. But note that everybody has a slight differentiation how they implement things, especially if you have such a big document or such a big yeah, document for the IMU here. Then people would try and read data whether from the gyroscope or the accelerometer in different ways. However, I have created a reference code which will be available in the description of this video here, which does rely on information from the datasheet. In this case here, the idea that we'll be implementing through this code here is quite simple. All we're going to do here is read the XYZ normalized data from the gyroscope, as well as the XLY's normalized data from the acceleration, as well as the temperature. The IMU also comes, the MPU 6050 here also has a temperature sensor. The temperature sensor is mostly used for its internal calibration. What I mean by that is that as part of the calibration cycle, included in for the calibration of the gyro as well as the calibration of the accelerometer, it detects its own temperature and uses that to be able to calibrate it properly. However, the the register for the temperature here is accessible, and that's how we can measure the temperature using it. It is not efficient for determining temperature though, because it is once again the temperature of the MPU, which after a while could heat up and will not be accurate of the actual temperature of the room. Going further with this IMU, of course, is not connected to the illegal target, so it needs in SDA and SCL pin. SDA and SCL is just data transmission lines as well as the clock line. These will allow for the I2C communication between the MPU 650 and the Arduino. The Arduino Uno only has one or has two set of SDA SCL, while the Uno would have it on the SDA and SCL pins that are right beside the AREF pin. And the Mega has also two, same idea for the AREF. The Uno has the second pair at A4 and A5 for SDA and SCL uh, respectively, as well as pin 20 and pin 20 on the Mega for the same thing. Something to mention here is that on the Lugo card kit, the SDA pins is not really visible in the camera here, but if you have it, you can see it on your device. However, I'm trying to point at it here. So there are the two end points here in the Mega. As you can see here, the shield is the shield for the illegal discovery. However, we do have space for a pin 20 and 21. There are the two green and white wires here. for the MPU connections. So this is the connection that we have here. You do need to install the wire and I2C dev as well, MPU6050 if you have not already done so. Just a quick reminder, you would just go and manage libraries and you find these libraries on there. Just to show you here, if I just open manage libraries, I can just search for the names in here. After, of course, it's updating the list. Just going on here, I can search for wire. And wire is now a pre-installed library for the Arduino, so it does not need to be installed from the library manager. We could also double check I2C dev here. Seems to be the same thing for the I2C dev here. So the I2C dev and the wire libraries do not need to be installed from the managed libraries, as most likely installed on your Arduino. However, that may not be the case with your Arduino, so it is a good idea to check. And then the MPU6050 does need to be installed. I am currently using the one by Electronic Cats. The Adafruit one is nice, but the Electronic Cats one by the one created by Electronic Cats is a better one and easier to use. After that, we declare a MPU object instance, which is simply seen here. Next here is we determine the accelerometer XYZ offsets as well as the gyro XYZ offsets. The way you would determine these is there are multiple ways to determine it. The easiest way is just go under File, Examples, scroll down. If you have less libraries than I do, then it will be closer, but you're just looking for examples from custom library, MPU 6050, and what we're selecting here is IMU Z0. Selecting IMU0 here, if you run this code, it's a pretty long code, so it takes quite a few minutes. But the idea here, what it does is it determines the offset using PID. And you can just read through the description here. The data that we printed will be something like this. And you would just use the data, either of the left or right data in the brackets here, and that will be your offset. Something I will show you in a second here, the offset doesn't actually make it go equal to zero. What the offset actually does is it makes that the average equals to zero, which I did create a go-to code that you're able to test that. Let's keep going with the setup here. First of all, we declare the serial communication. Now, if you remember from when we talked about serial in the previous video, serial communication does slow down the whether it's the void loop iteration or any process you're going, it does slow it down based on the baud rate here. That means that if you want to do any mathematical operation using the MPU 6050, namely just dividing by the sample rate, the sample rate is dependent on the actual speed of the communication between the MPU 6050 and the Arduino. However, the minute you add serial communication, that slows it down. You can increase that. Or you can basically remove the effect of the slowing down from serial communication by increasing the baud rate. By doing that, the serial communication becomes faster. Noting that you have to use a baud rate that works well with the Arduino. In case of the Mega and the Uno, you can reach up to 115200. Pretty big baud rate. If you are looking into Bluetooth communication, you have to also make sure that you use the proper baud rate that is either the default or what you can set at using the BT add commands, which which there is currently a video on Bluetooth communication as well that you can check out to be able to set this up. But so it is important that you have the correct baud rate. Otherwise, the data will be illegible, which I will show you actually just for the sake of practice here. And then we initialize the IMU. We need to start the wire connection. The wire connection is just, as I mentioned, the I2C connection. We just have a few serial commands here just to keep track of what's going on. We initialize the gyro. I named the MPU instance here gyro Excel temp just to show you what kind of data we can extract from there. And then we initialize it, of course. We just test the connection here because the MPU 6050, yes, because it is connected by wires, it sometimes glitches. It's quite frequently actually. It is so it is important to test the connection so be able to see that if it does glitch, you can just reset it. You can also implement various ideas here. You can either implement a watchdog timer, which will see it by itself, or maybe just connect or make it stop forever. We're using a while one loop. There's multiple ways you can work for this. I just left it as a serial command. We can just read it serially if there is an issue. I will also post a video on watchdog timers soon, so check that out if you want to implement this. Finally, we calibrate the gyro. If you do not include anything in the brackets here, the default is 15 loops as as part of the documentation of the library here. That's how they set it up. And then we do the calibration, we complete it. Then we set the gyroscope offsets and that we just mentioned above there. And then we have to calibrate it again. If you do, and you just need to, it's fine tuning, so you do not need all the 15, so you can just put a number to reduce it. But what it is important to note, if you do not calibrate it after setting the offsets, it may not necessarily work. You do need to calibrate it after setting the offset. That is how the setup is. It does take a bit amount of time, and you have to make sure that the code, the robot, or whatever where the MPU 6050 is completely still. If it is not still, as if it reaches a certain threshold, it will not take in the data, and it will show you through serial communication, which I will also demonstrate. However, let's go to the void loop here. It's quite a simple what's going on, how to extract the data. First of all, we declare the float instances here, and then we just use the specific function. So to get the temperature, we get the temperature data. Now, according to the data sheet, the how the registers are set up is after you extract the raw get temperature data, you need to divide it by 3040, and there will be a 3653 degrees offset, so you need to add that to be able to get a proper Celsius reading. Same thing with the gyro accelerometer temperature here. You need to divide by 16384 to get it in G. G is just stands for gravity, which is above 3.8 meters per second square. So 1G is 3.8 meters per second squared. Going for a gyro here, same idea. We take the, the raw data here, we divide it by 131. And that's why I mentioned it is important to read the data sheet because these are mentioned in the data sheet. And if you open, like, for example, the MPU 6050 example for the raw data, for example, where it just extract the raw data, it doesn't show you that you are able to divide by a certain value to get the proper data because as the name implies here, it just gets the raw data. So that's why it is important to read the data sheet. Not everybody implements everything the same way because not everybody will be doing the same thing you are doing. Anyways, so keeping going with this, we're just going to print it serially so we're able to read it. So that looks good. There seems to be no issue for you always need to save. So just by pressing upload, it does that and then compiles the sketch. No issues here. It's going to upload and it is completed and uploaded. So if we open the serial monitor here, and just for the sake of practice, and I keep it at the default 960, and I show you that here, you can see that the data looks, it's very illegible, it's pretty weird, it sends weird data. The first line you see up here is normal. Each time you open the serial communication at a different baud rate than 9600, that is because the default is 9600, and then the serial communication will change it after. In this case here, we changed the baud rate to 38400, if I remember correctly. Let me just double check here. Yes, that is correct. So we just set this up here. And then as you can see here, it's calibrating. Every dot is a calibration. If I just move it, and it will detect that there is a improper reading, and the star here means it ignored the data. And then now it just complete the first part here is calibration of the accelerometer, gyroscope, and now it's printing out the data. Now this is too quick to be able to read properly. As you can see here, the X and Y are 0. which is the proper way to demonstrate the data here. The x and y should be 0. The z, however, should be 1. And to think of it, how the IMU works is, think of it as a box, okay? And the box has a ball in the middle. Each time it moves, the ball touches one of the corners of the box, right? So there's 6 faces to the box. The top and bottom will be z-axis. About the face on the top will be positive z, but face at the bottom will be negative z. Same thing for the x and y on the right and left, and then for x on the right and left, and then y for the front and back. So if the box is left in free space, it may not be understood why is z equal to 1, but it makes complete sense. Gravity is acting on it, right? So if you leave any box on the bottom, it's actually always free falling to gravity. That's how the IMU works, because that means that the box is always pulling down while the ball is staying where it is, right? So the box is going down, so that means that it will touch the upper plate, and that's why z is positive. Okay, usually when we think of gravity, we think as negative 9.81, especially if you took your physics courses here. But you have in the IMU, Z is positive because of how the property of the IMU works. Now there is noise here, especially it is more evident in the gyroscope. As you can see, X and Y and Z gyroscope should all be 0. The thing is not rotating, right? So if you notice here, there is a slight value here. This is usually compensating by divided by the sample rate. The sample rate is quite huge, 8,000. So if you take the small value and divide it by 8,000, all these small values here are ignored. But it does accumulate error, especially if you're using it for a long time. So you have to think of various ways to reduce the error or not to avoid the noise here. There is quite a lot of ways to do that, whether you use a counter that prevents any increment for a certain amount of time, or maybe instead of calculating for a certain degree, let's say you're calculating for 360 degrees, you calculate per 9 and add 4. Stuff like that will assist you in reducing the error. And then just remember that you can also reset it at any time. So any accumulated error will reset. So there's multiple ways to think of this. That's why it is important when you work with the MPU6050 that you test a lot. Do not leave any project that you're working on this in the last minute, because you will have a lot of errors to account for. The temperature, as you can see here, is the temperature of the device. If the device has been running for a bit of time here, you can see that it increased a bit from what we saw, 24 on 40, now it's 2460. The temperature of my house here is about 24 as well, so it's very close. Some noise are starting to accumulate on the accelerometer, which is okay. So and then let me show you if I hold the robot up. So I will rotate it a bit and lift it and move it around, and then I will stop the auto scroll, and then we can see it together. So what we can see here is I'm lifting the robot, I'm rotating it, and then I'm putting it back down. I can also move it right or left, and then put it again back down. And then we can just look at the data we have here. So it is fairly quick, but we look at the data here. If we move up, that means that imagine the ball again in the box. That means the ball is now approaching or starting to go away from the z-axis towards the negative z-axis. So that means that it will not be 1 anymore, it will be less than 1. And as you can see, that is happening here. It is moving to be less than 1. And then we did next is we rotated it. So the axis of rotation here, if I hold my robot like this axis is dead, okay? This way is this way is positive and this way is negative. So turning left is positive and turning right is negative. It is not intuitive, but that's how it is. And then we have the x-axis like this. So this is the x-axis here. And then the y-axis is forward and backward. Now, if you look at your IMU here, you will see that there is a slight drawing at the very bottom where it says X and Y, the Z is not there, of course, because it is not possible to draw 3D on any board. It is a 2D drawing. So in this case here, that is the axes. I will upload a picture at the end of the description here where you can see where it may just record, it has the values of the axis, positive and negative, just for your reference. However, it isn't, you could just test it as well using just a simple code like this, which will also be available in the description, and just determine where the X and positive Z, X, Y axes for all of them are. So this is what we have here. You can keep testing it. You will see that the data keeps changing. And as such, this is the MPU6050. Now, as I mentioned at the beginning here, you can check if, let's say, the offset is set properly. Now, when the offset is set, as long as no power is lost for the MPU6050, then the offset will stay the same no matter what code you upload. Now, I did remove the ground communication max in here, so I will just re-upload this code. And then we can just open the IMU Error Determination code. So this code, what allows you to do is just test for various errors. Now, the most significant one that we'll see here will be the the average. However, you can use this to build different types of filters, whether you want to build a maximum minimum filter or using just to ignore sounds, or you can just use it however you like. There is quite a lot of significant data here that I developed. Now, I did set it to be 30,000 numbers of cycles per test. Just for the sake of speed here, we're going to reduce it to 300. The more tests you have, of course, is the more accurate the data. If we just upload it here, and then we're going to open serial communication when it's ready. Now this baud rate is also at 38400, running through the calibration again. So in this case here, I forgot to mention the thing. So this code here tests for 1 degree of freedom at a time. This just reduces the errors and the slower communication from the serial commands. So the x-axis of accelerometer is set at 0, 1, 2, 3, 4, 5. So whatever you want to test, let's say we want to test Z, for example, the Z axis of the gyroscope. We can just set this at 5 here as implemented from the table. Then we can re-upload the code. And then we can launch the serial monitor here. So once again, what this test does is it collects every test here, collects about 300 inputs of data, and then does that 20 times. So that accounts for about 6,000 data inputs. So conducted ZSS, it tells you what axis is testing here. The optimal value for the when still, so when at rest, is 0 meters per second. So the absolute value, the absolute highest value recorded out of all these data here is 0.33. The absolute lowest is negative 0.32. The average of the highest value from all tests, which means that if you look at the highest value from all the tests here and you just find the average, it's about 0.26. And the average of the lowest value from all tests is, again, the lowest value 0, be well negative 0.25. And then the absolute highest value of average highest value is above optimal. So that means that what it does here is it records all of the highest value and determines the average for it. And that is about 0.09. And then this is the highest. So out of all of these, that would be the highest here. And then the absolute lowest value of average, lowest value below optimal, Same idea, it records everything that is below optimal. So in this case here, below 0 meters per second squared, and it records that. So you can use these data dimension to build a filter if you would like. But important to note here is the average of all values, which is what the offset does, is 0. So out of all the 6,000 data here, when you add them all together and you determine the average, it is accounts to about 0. So the offset is working. This is what I meant to show you here. But you can use this for however you like. And then you can also test that the highest value above optimal is about 0.07, and the average is about 0.07 above optimal and negative 0.08 below optimal. So you can see here that the average is correct here. So um, in this case here, once again, it does set the offset here for you, and it is important to note here that you can determine the offset at any time using the example that I mentioned earlier in this video here. Um, but note that when you do the offsets, once again, you need to remember to calibrate them. And so that should be ready to go here. If we can test another one, let's say maybe the x-axis of the accelerometer, and just upload that. Now open the serial monitor here and just wait till the calibration and test is complete. So the idea for the accelerometer here is something to mention. Sometimes the accelerometer, for some reason or another, does not detect the proper input. Now there might be two reasons for this. Either I didn't either the calibration is incomplete, which is a common mistake that I wanted to show. In many cases here, a lot of people would just calibrate the gyro or one of them and forget to calibrate the other one. So in this case here, we need to remember to calibrate the accelerometer as well, because once again, if you do not calibrate it, the offset will not be inputted properly. So if we just include the calibration for the accelerometer in both cases here, if you do that and you still see a non-zero average, then that is the case where you will have to account for it in your code. That's what this code is also can help you do. So just completing the serial communication here. Now, as you can see here, after you do a proper calibration, it is accounts to 0.00. So that is what I want to show for the MPU 6050. As I mentioned, just make sure you practice with it a lot. It's a very powerful device. It does accumulate error though. I would recommend that if you will try and use this to determine distance, it does become significantly harder because you do have to divide by the sample rate twice, which means there is much more error that could be produced from that. However, feel free to play around with it, get to know the MPU 6050. It is a pretty powerful device, and see you in the next video.